Okay, so let's go ahead and talk about the assumptions behind the test. Every statistical test has assumptions, and so we should discuss the assumptions for a paired sample t-test because that's what we're learning here. So the very first thing you should notice with the assumptions is that the first three assumptions are exactly the same as the previous two hypothesis tests that we've learned, the z-test and the independent sample t-test. So those first three is that the dependent variable should be a scale variable. It should be interval or ratio. The second one, that observations are randomly selected from the population, you should know as well. So we were assuming random selection. And then the third is that our population should be normally distributed. And so in this case, if we're talking about groups, in this case our independent variable is nominal, then we can use our central limit theorem to help us in determining whether or not the populations are normally distributed. So just like we would with a z-test or a single sample t-test. So the first three assumptions are exactly the same. The fourth one we've already talked about as well. The observations should be dependent on each other. So it should be within groups design, or samples should be dependent. And so we've talked about that one already in this lecture. And then the last one we haven't talked about yet, and we should spend some time to talk about, is that our population mean difference should be 0. So note that this is different than what we've had before. So before we've had some sort of population information to put in there, but remember now we don't have any population information. So we don't have a mean, we don't have any standard deviations for either of the populations, but we can still make an assumption. The assumption that we can make here is that if our two groups are the same and we subtract them from each other, then the mean difference in the population should be 0. So it doesn't matter what the mean is in each of the populations. If that mean is the same and we subtract them, then we should get 0. And that's what that last assumption is saying. So in our example of the prep course, that if the prep course has no effect, in other words, it does not increase SAT scores, then our sample with the no prep course and the sample with the prep course should have the same mean. And if they do, then the difference is 0. So we'll set the center of our distribution at a population mean difference of 0. And that's that last assumption. We're saying that there's no difference between the two populations if the two populations have the same mean score. So let's go ahead and talk about this last assumption in a little bit more depth. So this last assumption introduces a new distribution. So before we've talked about the distribution of scores when we're getting z-scores. We've talked about the distribution of means when we're getting when we're using a single sample z-test or a single sample t-test. Now we're going to talk about the distribution of mean differences. So there are three distributions that you should know now: the distribution of scores, the distribution of means, and the distribution of mean differences. We'll introduce another one when we talk about independent sample t-tests, but we have three distributions that we should know at this point. Now, the distribution of mean differences is similar to the distribution of means. In other words, it follows the same qualities as the distribution of means. It's still a normal distribution. It's still centered at a t statistic of 0, and it's composed of samples, or it uses samples in this distribution. So it's very similar to the distribution of means. The only thing that changes is that the distribution of mean differences is centered at a mean difference of 0, and it will always be a mean difference of 0 at the center of the distribution. So a t of 0 equals the mean difference of 0. Now in our single sample z and t test, the distribution was centered at whatever the population mean was. Here we don't have any population means that have been given to us, and so we have to assume that the differences between my two populations is the same. In other words, if we subtract them from each other, we should get 0. And so it will be centered at 0. So with our SAT data, what we're really saying is that there's no difference, and this is based on the null hypothesis, so H0, the null hypothesis, that there's no difference in SAT scores by students who do or do not take a prep course. So the mean difference is 0. And so remember, with the null hypothesis, we always assume the null to be true, and because of that, our distribution would be centered at the null hypothesis. There's no difference in scores regardless of whether students take the prep course or don't take the prep course. And so our distribution of mean differences will be centered at 0. So here is what our distribution of mean differences would look like. Again, it looks like our other distributions. It's a normal distribution. It's unimodal. It's symmetrical. It has two tails. It's bell-shaped. So just like our other distributions, the only difference is that the raw scores is centered at a mean difference of 0 in the population. So note that in the rest of the distribution, we will have scores that are above 0 and scores that are below 0. And so realize that there is random fluctuation, and so we're never ever really going to have two populations that will cancel each other out with a mean difference of 0. So at some level there's going to be a difference between our populations due to measurement error or sampling error. And so we create our distribution centered at 0, knowing that in the population it'll never truly be 0 exactly. It's always going to be off a little bit from 0, but it should be very close to 0. Right? So if you look within one t-statistic above and below 0, we would expect 68% of the population. So we expect values around 0, even though it won't exactly be 0. When calculating the t-statistic for a paired sample t-test, we need to know three things. So here's our t-statistic formula. You'll notice it looks very similar. We're taking the means of samples minus the means of populations and dividing by the standard error. The only thing that's changed is that we now have a new subscript. It's called diff. In other words, the differences, because we're using a distribution of mean differences, so a new distribution. So essentially in the numerator what we're doing is we're taking our two samples and we're subtracting them from each other to get a mean difference in the data that we collect. We then subtract the population mean difference. Now the problem here is that we actually don't know what the means are in the populations. But because of our fifth assumption, we can assume that the differences between those two populations based on the null hypothesis will be 0. That in the population, if there's no difference between the two means and we subtract them from each other, then we should get 0. So in this case, we'll take the differences of our samples, we'll subtract 0, which is the differences that we're assuming in the population, and then we'll divide by the standard error of the different scores from our sample. So the formula should look very familiar. It hasn't changed much. The only thing that really has changed is that we now can make an assumption about the population mean difference. The population mean difference we will assume to be 0. That means we can rewrite the t-statistic formula to be the mean difference of our samples divided by the standard error of the difference. So if we assume that the population mean differences are 0, that's our fifth assumption, then we can drop that from our equation and we're left with the mean difference of our samples divided by the standard error of the difference. To demonstrate how we get a mean difference, let's use our SAT and prep course example. So here we have Samantha, Greg, and Olga. We have them come in, we give them the SAT. We then give them a prep course and then remeasure them on the SAT. And so we have two samples here, one sample before the prep course and one sample after the prep course. And in this case, the dependent variable are their scores on the SAT. And so if I want to get a mean difference, I need to subtract the SAT before scores from the SAT after scores for each of my participants. So if I take Samantha's SAT score of 1250, so this is after the prep course, and I subtract her SAT score before the prep course, I get a difference of 250. And that's what we would call the X diff, or the X difference. I do the same thing for Greg and Olga, and I get a difference of 300 and a difference of 150 for Olga. And so now I have created a column of different scores, one for each one of my participants. I can now take the mean of those differences, and that's how I get the mean difference from my samples. So I had two samples, SAT before, SAT after. I subtract them from each other to get a different score, and then from those different scores I can calculate the mean difference. I can then use that mean difference and divide by the standard error of the difference. So note here, what we really did is that we took two samples, SAT before, SAT after. We subtracted the scores from each other for each one of the observations or each one of the participants. So remember that each of those scores are paired together. Each observation is being measured more than once. And we created a new column of different scores. Essentially what we did is we took two samples and turned it into a single sample of different scores. And so realize that everything we do from here on out is exactly the same as a single sample t-test. And so once we subtract our two samples from each other, then essentially all we've done is created a single sample where we'll now do a single sample t-test. And so don't make paired sample t-tests more complicated than they really need to be. Once we subtract our two samples from each other, essentially all we're doing from that point on is a single sample t-test. Okay, so here's our t-statistic. We get our mean difference, and we then need to get a standard error of the difference, and we'd get that standard error the same way as we would with a regular single sample t-test, except now we're going to use different scores. Our formula for the standard error would be the same as it is with a single sample t-test, but again, we're now using different scores. And so in order to get the standard error of the difference, I need to take the standard deviation of the difference and divide by the square root of the sample size. And now it's important to note here that in this case, the sample size is the number of observations that you have in your different scores column. So not the total number of values you have from the two samples, but rather the total number of values you have after you subtract your samples from each other. In order to get the standard error of the difference, we need to know the standard deviation of the difference. And so here's our formula for the standard deviation of the difference. You'll notice it looks a lot like the formula for standard deviation for a single sample t-test. The only thing that's changed is that we're now using the different scores that we calculated after we subtracted the two samples from each other. So we'll take each individual x value of the difference, in other words, each different score for each of our participants. We'll subtract the mean difference, square it, sum it together, and divide by the degrees of freedom. And so that formula is pretty much the same as it is with a single sample t-test, except we're using different scores. So remember, when we're doing a paired sample t-test, all we're really doing is a special case of a single sample t-test. We take our two samples, we subtract them from each other based on our observations. We then take those different scores and we conduct a single sample t-test. So there really isn't a whole lot that's different for the paired sample t-test. I think students sometimes get overwhelmed in thinking it's an entirely new test. It's not. We just do one minor thing. We subtract the samples from each other, and then we use what we've learned in previous modules. So to compute a paired sample t-test, we'll calculate a different score for each person or each observation. We then treat those different scores as a single sample t-test. And if you do that, then learning a paired sample t-test should go fairly quickly. Now again, we've talked about some conceptual things here today that you'll need to know conceptually, but mathematically it's very similar to what we've done in the previous module. Alright, I hope you all have a good evening, and I'll see you tomorrow in class.